Welcome everybody to one more iteration of our guest seminar series at Montréal MLOpt, and we are thrilled to welcome Sebastien Bubeck. Today is kind of a very esteemed colleague, kind of a legend at this point in optimization and many other TCS subjects. So it's very nice to have him here. His official position at this point is, I hope I don't mess it up, Sebastien, Senior Principal Research Manager at Microsoft.
Yes, I should stop adding, like, right? To this title, but it's okay.
Yeah, I wonder what the next qualifier is going to be. The sky's the limit. So today he's going to present to us a super interesting conjecture, it sounds like, on the explaining overparameterization as robustness for neural networks. Okay, and Sebastien, welcome, and we are all ears, and the floor is yours.
Thanks a lot for the two nice introductions. So I'm really excited to present this work in front of this virtual audience. I'm really looking forward to get your feedback, so please interrupt me with questions, with comments. It's going to be a mathematical talk, so it's really important for you to follow from one slide to the next, otherwise you're going to get lost. Everything is pretty simple, I think, so everybody should be able to follow easily, but please interrupt me and ask questions. Okay, so this is some joint work that I did last summer in pandemic summer 1 with two of my former interns, Yuanju Lee, who is now an assistant professor at CMU, and Dheeraj Nagaraj, who is a PhD student at MIT. And the work is titled Law of Robustness for Two Layers Neural Network. And really, it should be a conjectured law of robustness, as I will explain, and we don't know how to solve the conjecture. I will explain the conjecture pretty quickly in the talk, and if you want at that point to space out and try to solve it, please by any means try to do so. Okay, so what's the context? The context is adversarial examples. So adversarial examples, I think, are a real problem. And, in front of this audience, I don't need to explain to you what adversarial examples are. It's this very striking property of modern neural networks that they are very sensitive to a tiny perturbation of the input. So you apply a small perturbation of the input, and you can basically change the output to whatever you want. So you've all heard the joke of Alexander Madriz that neural networks can make pigs fly. By that, he means that you can have a picture of a pig, and you just apply a little transformation, a little perturbation, and the neural network is going to say that it's an airplane. It's a very real phenomenon. It applies to all neural networks. Anything we can do. Now, as I said, I want to give you a mathematical lecture. So for me, mathematically, I'm going to interpret this problem of adversarial examples as the fact that those neural networks are very non-Lipschitz. Okay. And what I want to ask is why? Why is it that those modern neural networks are very non-Lipschitz? Why is it that we can't seem to be able to train, very smooth functions? And the way I'm going to phrase it is that I want to ask if there is maybe some high-dimensional geometric phenomenon, just like we are very much used to concentration, maybe there is some other kind of high-dimensional geometric phenomenon that could explain why we're not able to train what I'm going to call smooth memorization machines. So smooth, I already explained, it's with respect to being Lipschitz. Now, why do I call them memorization machines? I call them memorization machines because I'm only going to be interested in the property of neural network, which is that they can, get zero training error. So of course, as everybody in this audience knows very well, this is extremely restrictive, and neural networks, they do much more than just memorize the data points. They have this very mysterious property of generalization. I don't want to talk about it. It's not going to be relevant to this talk. So for this talk, we're only going to be training about memorization, meaning zero training error. Okay. Now, what is going to be the upshot, of the presentation? What is our big claim? The big claim is that smooth memorization is actually much harder than non-smooth memorization. Okay. And what I mean by much harder, I mean that it requires provably, or tentatively provably, it requires much bigger models. So if you want to be able to smoothly memorize, you will need much bigger models.
We have a quick question by Simon.
Yeah.
Yeah. So here, I guess you wanted to have something that you can formally work with, but don't you think that it's normal that smooth memorization is difficult, and smooth generalization might be much easier than smooth memorization.
What is smooth generalization?
Well, I mean, that's because you don't want to just memorize the data, you want to be able to generalize. And so it's a much, yeah, I guess that's the idea. So that, because if you just memorize it, it wouldn't be sufficient. You want to generalize instead.
So I'm not sure I understood the question. Let me try to rephrase just quickly. It is absolutely true, and my goal to, I mean, my long-term goal, it's not going to be realized in this presentation, but to connect generalization and smooth memorization. So just memorization does not imply generalization, but presumably smooth memorization could have something to do with generalization.
So I guess here what you're saying is because they all have zero training error, they have to memorize at least, they need to be able to refit the training data that you'll call memorization. So even if you would have generalization, you would still need at least memorization in some sense. So
sure.
that's kind of the first step.
I mean, you know, it's like, it's a basic fact, I think, at this point, that training deep networks, they do memorize. I mean, they do feed the data, and you can train them even further, and they will generalize even better. And I don't want to talk about this part of the after.
Okay. Thanks.
Okay. But you know, I'm very happy to come back to this introduction slide at the end and see, you know, how you feel about it after the presentation, and maybe have a longer discussion at that point. Okay, so as Simon said, you know, I want to get formal. This is a mathematical talk, so let's try to get into it immediately. So let's say we have a function class script f of parameterized models, maybe, you know, multi-layers neural networks, and we're given a data set of pairs xi, yi. The xi's are d-dimensional vectors, and the yi's are, you know, real outputs. What is the memorization task? The memorization task is to find one model in this parameterized model class that memorizes the data, meaning that when I ask the model what is the value at xi, it reports yi. Okay, and everything that I say will apply to approximately equal. So in fact, it's not even really about memorization. It's, you know, it's just about fitting the data, everything that I talk about. Good. Now we're going to focus on a very simple but very important model class, which is that of one hidden layer neural network. So given a nonlinearity psi from the real to the real, the function class fk of psi is defined as follows. So I'm gonna have k neurons. Each neuron, what it does, so the else neuron, it computes a linear function wl.x. Then it applies the nonlinearity psi. Okay, so it first computes the linear function wl.x, then it computes the nonlinearity psi. That's the output of the else neuron. And then all those k outputs are recombined linearly with the coefficients al. So any function that I can represent like this is in my function class fk of psi. Now, why is this an important class? It's an important class because it's arguably the simplest universal class, meaning that with this function class, if k is large enough, I'm going to be able to satisfy the memorization task for any data set. Okay. Now, of course, a very basic question is how large k needs to be so that you can fit a certain given data set. Okay. So that's a very basic question, and this has been answered, you know, 30 years ago. So here is one example of a theorem that you can get for this answer. So if you use the step function as the nonlinearity, and as long as your data is in general position, so very important general position, let me remind you what it means. It means that if I look at any affine subspace, then on that subspace, I'm going to find at most d data points. I'm not going to find more data points than what is strictly required by, you know, the linear structure of the space. So there isn't any spurious linear correlation between the xi's. Okay, so that's data in general positions. Now, say your data is in general position and you have binary labels. Then what Baum proved is that it's sufficient to have a number of neurons which is larger than 2n over d. Okay. Now, let me comment on this 2n over d. First of all, I will not prove it for you, but it's a very easy argument that just from purely linear algebraic considerations, you can always fit a data set as long as k is larger than n. Okay, so you never need more neurons than the number of data points. That's the first very, very simple fact. Okay, it's purely linear algebraic, as I said. And what this theorem says is that, in fact, you need much fewer neurons in higher dimension. You only need number of data points divided by d. Okay, and this makes sense because notice that k times d is roughly the number of parameters that you need to describe a one hidden layer neural network, right? Because each neuron is parameterized by d plus 1 points. So the total number of parameters is k times d plus 1. And from, you remember from linear algebra that you roughly need number of parameters larger than number of equations to find a solution. So it makes sense k times d larger than n. Now, of course, maybe you don't like this. Yes?
Sorry, Sebastien, I have a question.
Yeah, I have a question for you, Seb.
Okay.
So the general position assumption, is it just for convenience because things are easier to prove, or is there something really bad that happens when the assumption doesn't hold?
There is something really bad that happens when the assumption does not hold. So if the data is not in general position, then everything could be on a line. Like the dimension d does not have any meaning, a priori, if you don't make any assumption. Like everything could be on the line, so you could be effectively in dimension 1. So there is no way that you can see improvement when the dimension increases. The only way you can hope to have dimension when the dimension increases to have an improvement is if the data really uses all the dimensions. Now, let me say it right away, like this general position assumption, it's really nothing, right? I mean, it's really nothing. Like you can apply infinitesimal noise to the data points, and this will put them in general position.
Yes.
But of course, something bad is going to happen if you do that. I will explain. Does that answer the question?
Yeah, it does. It does. But it's kind of, you won't be Lipschitz if you have infinitesimal noise.
Exactly right. You're jumping the gun of the next slide. Yes, absolutely, yes. But for this theorem, it doesn't matter. Yeah. So maybe you don't like the step function. Maybe you don't like the binary label. So here are two references. This is a triviality that I'm going to explain on the next slide. But still, I think those papers are the first ones that observed it. That if you use the rectified linear unit, then in fact, the same theorem holds with another factor 2 for arbitrary labels. Okay, so with the rectified linear unit, you can actually fit any labels using just a number of neurons, which is 4 times n over d. Okay, so since this construction is going to be so important for the rest of the talk, I'm going to explain this theorem. Okay, the proof is extremely simple, and we're going to do it together. All right, so the proof goes like this. The first thing to notice is that with the step function, you can write the indicator of a slab, so a little slab around an affine subspace w.x equal t as just the difference of 2 neurons. Just look at the neuron, which is the indicator that w.x is larger than t minus epsilon, minus the indicator that w.x is larger than t plus epsilon. So let's look at what happens. I'm at 0, and I'm going to move in the direction w. So I move in the direction w, and when I hit the subspace w.x is equal to t minus epsilon, then this neuron starts firing. So, I'm very close to the affine subspace. I'm at distance epsilon. This neuron starts to fire, but this neuron still does not fire. So I have value 1. And now when I reach, the distance t plus epsilon, then this neuron starts firing. So they cancel each other out, and I get 0. Okay, so this difference of 2 neurons is exactly giving me the indicator of a slab. So now how am I going to use this difference of 2 neurons to fit my data? Well, just using this slab, I'm going to be able to fit d data points. How do I do that? Well, just bundle, d data points with the same label. So let's say you have d data points with label +1. Because it's only d points, you can all fit them on an affine subspace. So this is, this black line here. And now I can use my 2 neurons to do the indicator of a slab around this affine subspace. So it's going to give me 1 on this entire green region. And the point is, because the data is in general position, I can make this slab thin enough so that it does not contain any other point. So this difference of 2 neurons outputs 0 everywhere else, and it outputs 1 on the slab. So, I can just keep building those difference of 2 neurons, and I will only need n over d of those difference. So in total, 2n over d neurons. Is that clear? Yes.
People seem happy. You don't see this, but they only seem it's okay, as we say. But if there are any questions, please let us know.
Sounds good. So now with the rectified linear unit, you can actually fit, not only can you do this step function, but you can do any linear function in the slab. Why is that? It's just because if you look at the derivative of a neuron, which is a ReLU neuron, you're going to have the step function part, and you're going to have a linear part. And using the linear part, you can do a linear interpolation in the slab. Okay, so you're just going to replace the step by a difference of 2 neurons. So that's why each step neuron is replaced by 2 neurons. So that's why you're going to need 4 times n over d neurons. Okay, so this is very, very simple. Now, of course, anyone this is a machine learning audience, so I hope you're outraged by this construction because it doesn't make any sense. This is a prototypical overfitting situation. Like it really just very narrowly fits the data points, and then outside of it, it says 0 immediately. So from a generalization perspective, like this is not going to generalize. If you make it very thin, and your distribution has a measure is absolutely continuous with respect to the Lebesgue measure, then it's just going to have terrible generalization. It's going to output 0 everywhere, almost everywhere. Okay, so in my language, because I don't want to talk about generalization, but I want to talk about smoothness, which is a much easier concept, I'm going to say that this construction is very non-Lipschitz. Okay, and as Gauthier pointed out, I said before that general position is not an assumption because you can always add infinitesimal noise. But of course, if you add infinitesimal noise, then the width is going to be infinitesimal, and then it's going to be really very, very non-Lipschitz, right? Note that I say non-Lipschitz, and maybe you're offended because the step function is itself very non-Lipschitz. It's discontinuous. But of course, I mean, don't worry about that. Think about a smoother version, or, when I talk about Lipschitz, non-Lipschitz, it's really at scales that matters. It doesn't matter that it's non-Lipschitz at very, very tiny scale. If that didn't make sense, this sentence, just ignore it. It's not important. Let's see now how non-Lipschitz this construction really is. So for this to give a notion of how non-Lipschitz it is, I need some model on my data. Just general position is not going to be enough to say anything interesting. So I'm going to assume in this entire presentation that I have well-dispersed data. So it doesn't really matter too much what I mean by well-dispersed data, and real data sets are well-dispersed. But let's say to fix idea, I'm going to assume that in fact the xi's are IID on the sphere. Okay, they are just uniformly distributed vectors with norm 1. Okay, so this is a real assumption, and we're going to work under this assumption. And of course, going beyond this assumption is very interesting. Now, here are the 2 pictures of what's happening. So what is the bound construction? I select a group of D points, and I make them go through a subspace. Okay, so that's what I do. So this is the picture. Now, it's very easy to do the calculation that this subspace, the inner product, the value of t in the w dot x equal t is going to be 1 over square root d. All the mass is concentrated in the width 1 over square root d. So this neuron is at distance 1 over square root d from the origin. But the problem is, in high dimension, in any direction, all of the rest of the data is going to be, in width 1 over square root d. So it means that the width of my bound construction better has to be, 1 over square root d. So you see that the slab is of width smaller than 1 over square root d. So it means I go from 0 to 1, even if I do a smooth version of the step function instead of the step function, if you didn't like that. But certainly with the bound construction, like really necessarily, I go from 0 to 1 in distance 1 over square root d. So the Lipschitz constant will be at least square root d. Okay, square root d, that's a bad Lipschitz constant. It's a very sensitive function. I can do a tiny perturbation and it's going to be blown up. Okay, I just move by distance 1 over square root d, which is a tiny number, and the function value changes by 1. All right, so that's we're not happy about that. Now, in fact, the situation is even worse. It's not even square root d, it's in fact d Lipschitz. So let me try to explain this. This is very slightly more complicated, but only very slightly. So I said that when I move in the direction of this neuron, I move the distance 1 over square root d, and I go from 0 to 1. That's true, but I have only moved 1 over square root d distance. Now I can look at another neuron, which is basically orthogonal to this one, and I can also move at distance 1 over square root d in that other neuron. And I can keep repeating that. And if I have d neurons, I'm going to move distance 1 over square root d for each of those d neurons. So in total, I have moved only distance 1, right? Because 1 over square root d squared plus 1 over square root d squared, etc., plus 1 over square root d squared d times, that gives me 1. So I have moved only distance 1. But what is the function value that I see? Well, I have activated d neurons. So the value that I see is d. Okay. So by moving distance 1, I change the function value by d. So in fact, I'm d Lipschitz. Not even square root d, I'm d Lipschitz. And you can show that this is actually tight. This is a real answer. The bound construction is d Lipschitz. Okay, this is a somewhat minor detail, but it will be, if you want, to make progress on the conjecture, you need to understand this and more refined version of this very soon.
Question in the chat.
Yeah.
There's a question regarding the importance of the finiteness on the number of data points.
That's an excellent question. So this talk is about the finiteness of the data points. So there is an entirely different literature about approximation properties. So when you talk about approximation, you want to approximate a certain function everywhere in space. And this is a completely different phenomenon. You can think about it as when you want to approximate over the entire sphere a certain function, it's effectively as if you had exponentially in the dimension many points. And this presentation is about polynomially many points in the dimension. And I would argue that polynomially many points in the dimension is the regime of interest. You're not interested in exponentially many points. That's like, yeah.
All right.
Does that answer the question?
Yeah.
Cool. Okay, so now the next slide is going to be, the key, the crux of why we conjecture that, why we make our conjecture, and the slide after that will be the conjecture. So let's see what happens. So the bound construction, which remember as a number of neurons, which is n over d, is, let's say, optimistically square root d Lipschitz. We've seen that in fact it's not even square root d, it's d Lipschitz, but never mind. But in principle, notice, and this is a key point, that random data, polynomially many points on the sphere, you can actually interpolate, you can memorize it with constant Lipschitz. So this is this picture. So let's say you have, d to the 5 points. So you have d to the 5 points uniformly distributed on the sphere. Then those points are very isolated. So you have a sphere of radius 1, and it's very easy to show, and I hope everybody is familiar with this phenomenon, that any point is very isolated from all the other points. Namely, if I draw a ball of radius, let's say 1 over 10, around any point in my data set, this ball is going to be empty. There will be literally no other data points in that ball. And, I think that makes a lot of sense. I mean, that's what you see with images, of course. So the points are very isolated. So it means that, I could do, like, if I want to interpolate this data set smoothly, I can just do a bump function, like this red function, around any fixed data point. So, I hope many of you are familiar with the fact that bump function is a technical term. It just means, whatever. It means this picture, that it goes smoothly to 0, in infinite amount of space, and all the derivative, like it's C infinity, it's everything you want. So you can, you're just going to go from 0 to 1 in distance 1 over 10. So this bump function is going to be 10 Lipschitz. And of course, those bump functions, they don't see each other. So I can just keep adding bump function, of the given height of the label that I want to see. And this is going to be constant Lipschitz. All right. Now, with neural networks, of course, I can mimic this construction. I will just need a number of neurons, which is of the order of the number of data points. Because, there are many ways to see this. Like this bump function, I can probably approximate it with just like 10 neurons or something, some constant number of neurons. In fact, you can literally build a bump function on the sphere with 1 neuron. You don't need, you don't need 10. But certainly in spirit, you can imagine that, these fixed functions, this fixed bump function, you just need a constant number of neurons. And you will need a bump function for each data point. So in total, you will need of order of n neurons. So let's recap. We have 2 options. Either you do the bound construction, and then you have a small model, okay, a small neural network of size n over d, but it's very non-robust. The Lipschitzness is at least square root d. Or you can do this more trivial bump construction, which has a very large model. It has a number of neurons which is of order n, but it's very robust. And of course, very naturally, the question is this a real trade-off? Do you really have to trade off the size of the model with the smoothness, or can you do better? And what we conjecture is that this trade-off is real, namely exactly the trade-off that I gave. That is, if you want to smoothly memorize, then we conjecture that you require overparametrization by a factor d compared to just memorization. So just to be clear, a factor D, so what I'm saying is you don't need a neural network which is 2 times bigger or 3 times bigger, you know. I'm saying you need it 1 billion times bigger or 1 million times bigger if your dimension 1 million. Okay, so really enormous overparametrization if you want to be able to smoothly memorize.
There's a question.
Yeah, let's take the question.
By Gauthier.
I was not sure about asking it or not, but let's do it now.
Yeah.
It's in the previous slide. Basically, your bump function, you said that you can do it with a big O of 1 neurons. I'm just have a hard, because is it because like you are working on the sphere? Because it feels like you need to control any direction, and so you may need big O of D neurons, no? To like make it vanish in any direction.
Okay. Actually, you got me there. Yes, that's a good point. That's absolutely correct. So you're right. So let me take this back, and let's just say, because we're on the sphere, you can actually do a bump like this with just 1 neuron. Because
this is what I was trying to visualize. But with the sphere, it works.
Yes. No, you're entirely correct. Yeah, that was a good point. Yeah. I mean, okay, I don't want to get too technical. It's not entirely true because I only care about the value at this center, basically. So I don't need the bump to be exactly the same thing as this bump in all directions. I can do a simpler bump. But anyway, it's not very important.
That's why I was hesitating asking this question, because I thought it would be maybe minor. I trust you, we can do it.
More bump discussion at the end of the...
Yeah, sounds good. Yes. No, but it's a fair question. Okay, so in fact, we conjecture an entire trade-off curve between size and smoothness. Namely, here is a conjecture. Okay, this is the key point of the talk. For well-dispersed data on the sphere, so meaning, let's say, IID xi on the sphere, we conjecture that there exists a target binary function, target labels yi. In fact, we conjecture it's true for most labels. Okay, so for random labels, for example, with the following property: any one hidden layer neural network with k neurons that memorizes the data, and in fact, this is also true if it approximately memorizes, it doesn't matter, must also satisfy that the Lipschitz constant, so the smoothness on the sphere, is lower bounded by a constant time square root n over k. Okay, this is a conjecture. We don't know how to prove it. I'm going to tell you what we know about it, but really, we really don't know how to prove it. Okay. Now, let's just recap the 2 regimes that we saw and to interpret this bound. So the 2 regimes that we discussed so far, and note that we only discussed upper bound, right? We have not said a word so far about lower bounds, are the optimal size regime, which is, k is of order n over d, number of parameters is of order number of data points. You cannot go below that to memorize. So if you are in this optimal size regime, what does the conjecture tell you? The conjecture tells you that the Lipschitz constant should be larger than square root d, right? Because k is n over d, so square root n over k is square root d. So you see, bound construction is not even attaining this conjectured lower bound, right? It's only d Lipschitz. So far, I haven't even told you a matching upper bound in this optimal size regime. And even the upper bound is surprisingly difficult. We'll do it together towards the end. And the other regime we discussed is this, putting a bunch of bumps. So that has Lipschitz constant of order 1. And what does the conjecture says? If this is upper bounded by 1, then k needs to be bigger than n. Namely, it's saying, that if you want to be constant Lipschitz, then the best you can do is basically the bump construction. So it's a very, very strong conjecture. And again, we don't know how to prove it. So let me say that the bound construction, you can play with the size of the bundle. And what you will see is that you can do a bound construction which uses k neurons, and the Lipschitz constant is going to be n over k. Okay, so n over k is worse than square root n over k, and actually having matching upper bound in all regimes is also open. But we have one matching upper bound in the optimal size regime, so a square root d when k is like n over d. I will explain. Okay, any question on the conjecture?
Simon has his hand raised. Go ahead, Simon.
Yeah, so here I am looking at your worst case on the labels, in the sense that, in some sense, like, we could think that there's a notion of complexity, that indeed, for the worst case scenario, you will need to have high Lipschitz constant. But for say well-behaved distribution on y given x, then you would not need this Heidisch constant.
Yes. So let me comment on that. So the first thing you need, which is very, very important to understand, is for any target function, there is a smooth interpolation, because my data is, well dispersed on the sphere. So every point is isolated. So I can always smoothly interpolate. Okay. So it's not an inherent property of the data. Like, the data is not difficult. You can fit the data smoothly. What this conjecture is about is that one hidden layer neural network cannot do this fitting smoothly using a small size. Okay, so it's really, is that clear? There is no difficult data here, but there could be especially easy data. That I agree with. So a next point that you might make is, maybe I want to assume some model of y given x. I agree with that. And, immediately you get into a very tricky situation. Namely, maybe it's reasonable to assume that, y given x is generated from a small and smooth neural network. But of course, if the data is generated from a small and smooth neural network, then there exists a small and smooth neural network that fits the data, right? So when you start to get into models about the y given x, I think what might happen is that maybe there will be algorithmic law of robustness. So this is another important point, like I want to put the spotlight on this, is that there is no algorithm in this conjecture. This is something about all neural networks. This is really, fundamental trade-off between size and smoothness. Now, maybe when you start to make assumptions about the target function, maybe what happens is that there exists a small and smooth neural network, but maybe it becomes hard to find. And of course, this is way beyond, what we can do right now. So in my view, this conjecture is like a baby step. It's the very, very first step you want to take in this direction. And we cannot even take that step. But after that, there are a plethora of directions that you might want to get into. One of them is, structure on the y's, but there will be many others that I will discuss towards the conclusion. Did this satisfyingly answer your question?
Yeah, so I still have one thing. So at the beginning you said, well, there are no hard functions here, so because they all can be fit with a smooth.
Yes.
But what's the parametric family, or what's the architecture for this smooth interpolator?
Of course. I mean, what you're asking is the point. The point is to say that there are certain architectures which are better adapted for smooth fitting. This is exactly the direction that I want to get into. Okay. And here, architecture, because it's one hidden layer, architecture is just parameterized by a single number, which is number of neurons. And I'm just asking, okay, in terms of number of neurons, what is the best architecture to fit smoothly data? And I'm saying I give you a precise prediction of how the smoothness relates to the number of neurons that you're going to use. But exactly, I mean, I exactly would like to answer your question. That's what the project is about, answering your question.
But because at the beginning you did give this construction which gave a small Lipschitz constant which fit. But this construction was not in this architecture. That was the problem.
It is in this architecture using k equals n.
Yeah, well, which is too big.
Which is too big, but the point is,
yeah, okay.
The whole point is going to be to say that it's too big, but too bad, because this is the best you can hope for. In the worst case, I agree. I agree. In the worst case over the binary labels. Yeah, perfectly fair.
Thanks.
Cool. So again, I mean, immediately we get into that a machine learning audience, an expert machine learning audience is frustrated by this conjecture because you want to say so much more. But the problem is we cannot even say this stupid claim. Okay, so that's my perspective, is that we first need to understand this one. So I'm going to tell you what we know about this law of robustness. Okay, we tried 3 different approaches: one geometric, one statistical, and one algebraic, and they all fall short, at various distance from the real goal. So the geometric approach is going to be like this. We're going to prove a lower bound, which is, instead of square root n over k, we're going to prove square root d over k. And I want to be upfront that this is a very weak result. It's a much weaker result. And you will see on the next slide, I will give you the proof why I say it's much weaker. And what's really important to understand is that it only says something in the under-complete regime, right? Square root d over k, it's non-trivial, meaning it's larger than 1, because of course you need to be at least 1 Lipschitz to fit random points on the sphere. So, you know, it's only interesting if you prove a lower bound larger than 1. So this square root d over k is larger than 1 only when k is less than d, meaning this lower bound only tells you something interesting when your neurons don't even span the entire space. Okay, and that's a very different regime where different things happen, and it's much, much simpler. The real question is about the over-complete regime, when you have, you know, I don't know, n is d to the 10, and you're using d squared neurons or something. Okay, that's the real regime of interest. Okay, so I will give you the proof, the full proof of this claim on the next slide. The next approach is statistical, which is, you know, I said I didn't want to talk about generalization, but of course it's very tempting to relate smooth memorization to generalization. And that's what this lower bound is going to do. I'm going to relate the Lipschitz constant to the Rademacher complexity. And I'm going to say that if you can memorize and your Rademacher complexity is bad, so your Lipschitz constant has to be bad. Okay. The problem is I'm not going to be able to really control the Lipschitz constant, but only an upper bound on the Lipschitz constant, a proxy for the Lipschitz constant. Namely, it goes as follows. So one hidden layer can be viewed as a linear function, A, the output coefficient, composed with psi, the nonlinearity applied coordinate-wise, to the hidden layer W applied to X. Okay. Now, an upper bound on the Lipschitz constant is going to be given by the chain rule, meaning the product of upper bounds on each of these components. You know, this is just a composition of 3 functions, the linear function A, the coordinate-wise function psi, and the linear operator W. So the Lipschitz constant of F is upper bounded by the product of those 3 Lipschitz constants, which is Lipschitz constant of psi, times the L2 norm of A, that's the Lipschitz constant of the linear form A, times the Lipschitz constant of the operator W, which is the operator norm of W when W is viewed as a matrix. And I'm going to relate this product of 3 numbers to the Rademacher complexity. So all of you know very well the Rademacher complexity of a function class F. It's 1 over square root n, the expectation of how well I can correlate with random noise. So the yi's are random plus minus 1s, and I look at how well I can correlate on my data set of xi's. This is the Rademacher complexity. Now, what you've all seen is in, you know, machine learning 101 is that the Rademacher complexity of one hidden layer neural networks is upper bounded by the Lipschitz constant of psi times the sum of the absolute value of the coefficient times the L2 norm of the weight vector WL. Okay, this is just an application of the Talagrand contraction lemma with the fact that the Rademacher complexity of a linear model is just the L2 norm of that model. Okay, so this is like super, super simple. So the Rademacher complexity of the Lipschitz constant of psi is upper bounded by the sum of those products. But I want to make appear the L2 norm of A and the operator norm of W. So let's apply a Cauchy-Schwarz. This sum of product is upper bounded by square root of the sum of the AL squared. So square root of the sum of the AL squared, that's the L2 norm of A, times square root of the sum of the L2 norm squared of the WL, that's the Frobenius norm of W. And now here is a very important step that we're going to use again in the algebraic approach. So it's important to understand it very precisely, which is that the Frobenius norm of a matrix and the operator norm of a matrix are related by square root of the rank. So W, because I only have k neurons, it's a matrix which has rank k, at most k. So the Frobenius norm of W is upper bounded by square root of the rank, which is square root k, times the operator norm of W. Remember this inequality, let me just remind you, it's by spectral decomposition, because the Frobenius norm, you know, you can just rotate the matrix and it will be diagonal with the eigenvalues onto diagonal. So the Frobenius norm is just the L2 norm of the spectrum. It's just square root of the sum of the eigenvalues, or, you know, singular values or eigenvalue squared, let's say. So it's upper bounded by square root of the number of non-zeros eigenvalues times the largest of them. So square root of the rank times the operator norm. Okay, so it's really because I have eigen decomposition that I can do this. And I'm really emphasizing this point because in the algebraic approach, I'm going to talk about higher order tensors. And matrices are tensors of order 2. And for higher order tensors, you won't have this inequality, and this will lead to some interesting phenomenon. But in any case, right now, what we have proven is that the Rademacher complexity is upper bounded by square root k times Lipschitz constant of psi times L2 norm of A times operator norm of W. But now, if your function class is rich enough to memorize, then it must be that the Rademacher complexity is larger than square root n, because you can perfectly correlate. So that's it. We proved that the product of these three numbers is larger than square root n over square root k. So that's it. That's the proof of the conjecture for a proxy for the Lipschitz constant. Now the whole point is about understanding, bridging this gap between the proxy and the real Lipschitz constant of f. What could happen is that you could very carefully craft your neurons so they have lots of cancellations between them, and the Lipschitz constant is actually much smaller than what it appears naively by taking the chain rule Lipschitz constant. Okay, so it's all about understanding, like the lower bound will be about proving that there cannot be such crazy cancellations. Okay, and last but not least, what I will tell you is the algebraic approach. So this is actually the deepest part of the work. So there we're going to assume that psi is a degree p polynomial. Okay, so with a degree p polynomial, you're not universal, you cannot approximate anything, but you can memorize d to the p points. Okay, and what we'll show is that in this regime where you're trying to memorize as many points as possible with a polynomial activation function, then it's going to correspond to some tensor. I will explain what tensor, being max rank, and the rank is going to correspond to the number of neurons, which is going to be d to the p minus 1. So we're going to be in the optimal size regime. Remember, the optimal size regime is a Baum regime, which is k is of order n over d. Okay, so k is d to the p minus 1, which is d to the p over d. Okay, so we're in the Baum regime, optimal size regime, and we're going to prove the conjecture for this case. And this is interesting because you see, we are here, we are in the overcomplete case. So on the contrary to the geometric approach, we're going to be in the overcomplete case. And on the contrary to the statistical approach, we're going to actually prove a lower bound on the real Lipschitz constant, not a proxy for it. But it's only going to be in this max rank case. Okay. So next slide, I will tell you the geometric proof. Very, very simple, you will see. And then I will have 2 slides on the algebraic approach and some cute connections to various parts of mathematics. And then I will conclude with some open questions. Is that good for a plan? Is there any question on this slide?
The plan is great. Simon is giving a very enthusiastic thumbs up.
Okay.
Let's see if there are any questions. Any questions so far from the audience? Okay, give them 5 more seconds for the shyer ones. Okay, people seem happy and ready for what's coming up.
Okay, so I will give you the geometric proof of square root d over k instead of square root n over k. And this is kind of trivial, as you will see. Why do I say it's trivial? I say it's trivial because, in fact, this lower bound applies to much more general models than just one hidden layer neural network, namely multi-index models. So remember from economics, like a single index model is just I have high dimensional data, but I'm only going to make decision based on the projection in one direction. Okay, so that's what economics like to do. But now you could think about multi-index models. So instead of just caring about one direction, I could care about k directions. So mathematically, it means that my function, my decision function f of x is going to be some function g, arbitrary, composed with p of x, where p is a projection on a k-dimensional subspace. That's a multi-index model. And the claim is that for any such multi-index model that memorizes random data on the sphere, it must be that actually the Lipschitz constant is larger than square root d over k. Okay, so of course this implies a conjecture for the square root d over k for neural networks with k neurons, because if I have k neurons, then I'm only care about the projection on these k directions. Okay, so you see it's really a very geometric property just about the fact that we're only going to vary on the k-dimensional subspace. So maybe instead of actually giving you the proof, let's just say it in words, because it's really very, very easy. So what happens is I have the sphere, right, in dimension d. If I project the sphere in a direction, you know that most of the mass is going to be concentrated in a radius of 1 over square root d. Okay, so really when I project the sphere into one direction, I see a much smaller sphere. I see a sphere of, you know, radius 1 over square root d. And if I project it on a k-dimensional subspace, then, you know, in one direction it's going to be 1 square root d, in the other one 1 over square root d. So in total, I have shrunk the sphere from radius 1 to radius square root k over d, right? Square root of 1 over square root d squared plus 1 over square root d squared, k times, so square root of k over d. Okay, so when I project on the k-dimensional subspace, I have shrunk the radius 1 sphere to radius k over d. But now I need to move on this shorter sphere. I need to move from labels -1 to +1. So in distance square root k over d, I need to move by 1. So it means that I'm at best square root d over k Lipschitz. And that's it. That's the proof. Now the only catch is that I'm projecting the sphere, but it's not the entire sphere that I care about. It's the training point. And the direction, the k-dimensional subspace that I choose, I'm going to choose it based on the points that I'm seeing. So you need to be just a little bit careful because, you know, you cannot argue like you would usually. So anyway, I do it here on this slide. Maybe I will share the slide. It's really just an exercise, you know, and anyone can do it very easily. It's really not a problem. Okay, so it's just about the fact that you project the sphere and it becomes a smaller sphere, and you still need to vary from -1 to +1. So you're going to be at least square root d over k Lipschitz. So it doesn't capture what we're really trying to say.
I have a question about the usual suspects.
I have a very quick question, Seb, about your intuition. When you project the sphere, don't you get a ball instead of a sphere of radius?
You do.
So, okay, because then your argument was, you have a new sphere of radius blah, but you have not a sphere, you have a ball, so points can be.
So it's even worse because
it's even easier.
Yeah, it's even easier because that means that points are even closer. So you know.
Oh yeah, because you want a lower bound. Okay, sorry, thanks.
Exactly right. Yeah, but your good catch. It is going to be a ball and not a sphere. Yeah, absolutely. Cool. Okay, I will share this slide if you want to see. Anyway, it's in the paper also. I mean, here for the slide, I made a simpler argument, in fact, than in the paper, but it doesn't matter. Okay, so that's all I want to say about the geometric proof. You see that it's really not capturing what we are really talking about. I mean, it's a silly thing. So let's get into the real stuff. And by real stuff, I mean, this is the only place where I actually know how to bound the real Lipschitz constant in a real regime of interest, meaning overcomplete, and it's a real proof of the real conjecture. And it's for polynomial activation functions. For the talk, I'm only going to talk about power activation functions, so just of the form t to the p for some integer p. And let's warm up with the quadratic case. Okay, so psi of t is going to be t squared. So in that case, what does a one hidden layer neural network looks like? It looks like the sum of al psi of wl dot x, which is a sum of al wl dot x squared, which is nothing but a quadratic form in x. So I can rewrite it as a Hilbert-Schmidt inner product between a certain matrix sigma and the outer product XX transpose, okay? Where sigma is this matrix, is the sum of the AL times the outer product of the neuron, AL, WL, WL transpose, right? So are we're all good with this notation? So this is just the inner product over matrices when you view matrices as vectors, and this is valid because, you know, it's the same thing as a trace, and the trace commutes, so, okay, it's just usual. And the point is now, okay, what's the whole point? The whole point is that a quadratic network, you know, rather than thinking about the neurons individually, I can really think about sigma. It's entirely specified by sigma, the underlying matrix. So there is an underlying matrix, and that's really what characterizes my one hidden layer quadratic network. And the Lipschitz constant of this function is very, very easy to check that it's equal to the operator norm of sigma. Okay, so the operator norm of the underlying matrix is what's going to give me the Lipschitz constant. And now the point is the inside, the one line, you know, it's always one line. The one line is as follows of how we're going to lower bound sigma. What we're going to prove is that for polynomial network, memorization implies that the network, and what I mean by the network, as I just said, is the tensors that represent this network. In this case, for the quadratic case, it's just this matrix. So this matrix sigma, we will see that when you memorize, you need to correlate sigma with a certain small random quantity. I will explain what is this small random quantity. And then if you as a network, you correlate with something small, then it means that you must be big to compensate for the smallness. So that's how we're going to prove things. Let's see what is the random quantity that we're going to correlate with. It's just this matrix, omega, which is a sum for I equals 1 to n of yi xi transpose. So why do I correlate with this? Well, I know that I memorize. So sigma times xi transpose, this must give me yi. So sigma times yi xi transpose, this must give me 1. So sigma times the sum of yi xi transpose, this must give me n, which is this thing. Okay, so the inner product, the Hilbert-Schmidt inner product between sigma that represent my network and this omega that represent my data, if I memorize, that must be n. Now, why did I say that omega is small? Omega is small because I want you to think about it as a random walk over rank 1 matrices. I have this rank 1 matrix x1 transpose, and either I'm going to do plus x1 transpose or minus x1 transpose. Let's think the yi's are random labels. And then I have x2 transpose, and I'm going to do, x2 transpose or minus x2 transpose. And I do this random walk over rank 1 matrices. And because it's a random walk, there will be lots of cancellation. Sometimes I will go to the right, sometimes I will go to the left. Of course, right and left is in the space of matrices, but okay, you get the spirit. So I will have lots of cancellation because of this random walk behavior. So because of those cancellation, omega is going to be small. So if sigma times omega is large, which is n, then it will mean that sigma has to be large to compensate for the smallness of omega. To witness this trade-off big-small, I'm just going to use Hölder's inequality. I'm going to say that the inner product between sigma and omega is upper bounded by the norm of sigma times the dual norm of omega for any pair of primal dual norms. So, what are the norms that we like on matrices? Of course, the Frobenius norm, okay, just the Euclidean norm. So in that case, the dual is just the Euclidean norm itself. Another pair that we like is the operator norm, which is, exactly what we want to bound, right? We want to lower bound the operator norm. So you see, with this inequality, I immediately get that the operator norm of sigma is lower bounded by n divided by the dual of the operator norm of omega. What is the dual of the operator norm? It's a nuclear norm, right? It's the sum of the absolute value of the eigenvalues. Okay, so I could study just the nuclear norm of this random walk over rank 1 matrices. This is very classical, very easy to do actually. But in fact, we could even just do it for Frobenius norm and use again the fact that the operator norm and the Frobenius norm are related. So it's a trivial exercise to realize that the Frobenius norm, let's say squared of omega, is less than n. So the Frobenius norm of omega is less than square root n. So we get that the Frobenius norm of sigma is bigger than square root n, right? But recall, we have already said that the operator norm is bigger than the Frobenius norm divided by square root k. So we immediately get, again, sigma is rank k because it's based on my k neurons. We immediately get the conjecture. We immediately get that the operator norm of sigma is lower bounded by square root n over k. So that's it, just by studying the Frobenius norm of this random matrix, we get the conjecture. But in fact, there's one more sentence on this slide, and it's a deep sentence, and I don't know the full reach of that sentence, which is that we can obtain an even bigger lower bound, namely by instead of studying the operator norm, instead of studying the Frobenius norm of omega, we can study the operator norm of omega. Okay. And then you can just do a few lines of algebra, and what you will see is that you can actually prove that the operator norm of sigma is larger than square root n over k times square root d over k. So square root d over k, it's a term which is bigger than 1, right? Because k, the rank, is always less than d. I can have at most, d neurons. It doesn't make sense to have more than d neurons. So what this is saying is that there is actually an even stronger law of robustness that holds for quadratic networks. It cannot, if I'm using a low rank matrix, okay, so if I'm using less than d number of neurons with a quadratic network, then I cannot even attain what the conjectured smoothness is. I'm even bounded away from it. Okay, so why do I say it's deep? Because as we'll discuss in the open problems, the law of robustness, you can take it in the direction of studying, more complex models, maybe multi-layers neural network, but you can also take it in the other direction, studying simpler models and seeing whether for simpler models, maybe there is an even stronger law of robustness that holds. I will talk a little bit about kernel methods. Now, what this is showing is that for the simpler case of one hidden layer, but with a quadratic activation function, then yes, there is an even stronger law of robustness, square root n over k times square root d over k. Did that make sense? And is there any question on this slide?
I see a hand. Go ahead, Adam.
I think it's a very cool proof on that slide. So thanks for showing that.
Yes, thanks, Adam.
The math side of me is happy, and as you already, I won't keep saying, the machine learning part is not happy, I guess. But keep going.
Okay, so that's a problem, because next slide I move to tensors. So the next slide is important and it has a lot of meat, but I won't get into too much detail. So you can just listen to it and see how you feel about it, but it doesn't matter that all the details are clear. So let's say that now you take an activation function which is a power p instead of just power 2. So f now is of the form sum of ALWL dot x to the power p. So then, just as this was a quadratic form when p is equal to 2, this is another sort of form. It's really a tensor applied to x, tensor p times. And t is just a tensor sum for L equals 1 to k of AL WL tensor p times. So now my neural network, instead of being represented by a matrix, it's represented by an order p, a p-dimensional tensor, which is this thing. Now, the point is I can repeat the exact same argument as before. T, this underlying tensor, is going to correlate with a random tensor, which is now a random walk over rank 1 tensors. And just like before, T times omega is going to be n. And so by Hölder's inequality, for any pair of primal dual norm over tensors, I have the norm of T is larger than n over the dual norm of omega. Now, I could try to mimic what I did before, where I tried to study the Frobenius norm of omega, and then I lower bound, the Frobenius norm of T. This is fine. It's very easy to study the Frobenius norm of omega. But now the problem is, as I have, brought your attention to before, is that in the quadratic case, we use that the Frobenius norm of a matrix is more than square root of the rank times the operator norm. And this is not true for tensors, okay? So I cannot just, control the Frobenius norm of omega and get something about the operator norm of T. And it's very deep and very interesting to understand what happens, what is the relation between the Frobenius norm and the operator norm over tensors. Let me just say to, whet your appetite on this, that a beautiful counterexample to this inequality is to look at the matrix multiplication tensor. So this is a tensor that acts on matrices instead of acting on vectors, and it's such that T, the tensor T, when I apply it to ABC, 3 matrices, it gives me the trace of the product ABC. Okay, so it's really about the matrix multiplication. Another way to think about it is that if I look at the slice, the last slice, just like I can slice a matrix, when I put in the first 2 arguments A and B, then in the last slice, I'm going to see A times B. Okay, so it's really the operator that represents the computation of matrix multiplication. And the fact that you can do fast matrix multiplication is the fact that this tensor has low rank. There is a low rank representation, okay? So anyway, you can study this and you will see that it's just not true, this upper bound. It's super simple. Okay, but what is true is that in fact, the max rank version of this upper bound is true. So it is true that the Frobenius norm of a tensor is more than square root d to the p minus 1 times the operator norm, and d to the p minus 1 is the maximal rank that a tensor can have. So, a matrix has rank d at most. Now a tensor, a 3-dimensional array has dimension at most d, has rank at most d squared. The 4-dimensional array has the rank at most d to the 3, etc. So basically, you can redo this proof, and it will prove the law of robustness for psi of t, which is t to the p, in this max rank case, when k is d to the p minus 1, meaning we are in the optimal size regime where n is d to the p and k is n over t. Okay, good. Now, last but not least, before I move to the open problems, I promised to you that I would show a matching upper bound to the lower robustness. So recall that the bound construction we saw at the very beginning has Lipschitz constant n over k instead of square root n over k. Okay, so this is like really painful. I mean, you would like, you know, the whole, we're talking only about lower bounds, but we don't even have a matching upper bound. So it's pretty, it's a real disaster. But I will show to you that you can get an upper bound at least in the optimal size regime where k is n over d, and it's surprisingly difficult, and it's using tensors again. So I will quickly show it. So here, this paragraph is just saying again that Baum is not optimal and we're not happy about it. So let's see an optimal construction. Let's say n, the number of data points that you're trying to fit, is some small constant epsilon times d to the p. So I want to be in the optimal size regime, so I'm going to be allowed to take k, which is n over d. That means d to the p minus 1. And what I suggest to do is let's take a neural network with the activation psi of t to the p, such that the underlying tensor t is the following. It's the sum for I equals 1 to n of yi xi tensor p. So here is a small calculation that shows that this tensor indeed outputs on xi, it outputs yi up to a small error epsilon. Okay, so it doesn't exactly memorize, but approximately memorizes. Now, the point is, you might say, but this tensor t, I can represent it as n neurons, right? For each data point, I have a neuron, which is xi to the p. But the point is, because of the algebraic structure, I know that I can rewrite this tensor using only d to the p minus 1 neurons. That's because the rank of a order p tensor is at most d to the p minus 1. So there is some other rewriting using only d to the p minus 1 neurons of this tensor. And that's what we propose to use to match the conjecture lower bound. Okay, and it's easy to see that the operator norm is what you want to get. Okay, did that make sense? So this is the matching upper bound in the case of the optimal size regime. All right, let me move on to the open problems. I will conclude with that. So the first one is, of course, prove the conjecture. Again, let me remind you, Lipschitz constant is larger than square root n over k for any k neurons, 2 layers neural networks that memorizes random data on the sphere. Less ambitiously, I talked about the fact that we can prove for polynomial activation the conjecture in the max rank case. Try to prove it in the low rank case, but you're going to hit a very serious obstacle whose name is matrix multiplication tensor. Prove a matching upper bound in all regimes. I still to this day cannot believe this is a difficult question. Maybe I should try again, but it's really incredible that it's hard to prove. And again, the only construction we know right now is either in the optimal size regime where k is n over d and it's this complicated tensor, presumably complicated tensor construction, or in the optimal Lipschitz constant, and there it's really trivial, it's just this combination of pumps. So maybe there's some way to interpolate between those two constructions, I don't know. Of course, is there a more general phenomenon, What is, like you can just ask for some model class script f, what is the lower robustness there? And as I said at some point during the presentation, you can take it both for more complicated F, multi-layers neural network, but you can also take it to simpler cases, like kernel methods, or other simpler cases. And there, presumably, there would be an even stronger lower robustness, like that you cannot even match what one hidden layer neural networks do. Now, maybe for the more complicated model classes, it's very plausible that maybe there is no lower robustness there. Maybe when you go deeper, optimal size neural networks can already smoothly memorize. By the way, this is a fantastic and absolutely approachable question. I don't know the answer to. But maybe when you go to more complicated classes, there begins to be an algorithmic lower robustness. Namely, that there exists a neural network that could fit smoothly, but it becomes hard to find. Okay. And of course, all of this is in the context of adversarial examples. So, let's solve adversarial examples. Okay, I'm going to stop here and maybe take more questions or comments or more discussion. Thanks.
Thank you, Sebastien. Let's thank our speaker.